use Dan over here. They're scientific for the lab, Professor Models, and remember JPE. Dan does a lot of work that brings together a lot of different topics and scientific and technology. I know today, as we talk about black holes in the early universe, he's also engaged in a lot of scientific communication, various books, magazine articles, podcasts. He also has a textbook coming out this spring titled Particle Technology and Astrophysics. He's visiting for the rest of the week, so please, if you haven't signed up and are interested, please sign up with him. But for now, let's hear Dan's Blackboard talk.
I just want to thank everyone here who has made me feel so at home while we visited this week, especially the students who took me out for karaoke last night. Special thanks there, and David for organizing that whole adventure. So I'm going to talk about the ways in which primordial black holes could have changed the thermal history of the early universe. These are a series of papers that my collaborators and I have written on this and related stuff. I'm not going to reference those throughout the talk very much, so just if you want to know more details, that's kind of where to look. Some of these collaborators, just to give a shout out, are Gordon Kroniak, Sam McDermott, Nikita Blenov, who you guys have down the street in New York now. Celeste Keith, my former student, or Ireland, one of the students I'm working with right now. John Mark Russell, Albert Stevens, and Ruben Johnson. We didn't start from scratch. These papers, although they have novel elements built on previous work, some of the most important work was from Barrow et al. Back in '91, Bauman et al. 2007, and more recently Morrison et al. in 2019. Let's talk physics. So here's what I have in mind for my initial conditions. Something like inflation happens, reheats the universe as some sort of hot bath of radiation. In this stage, the universe is pretty much homogeneous, but there are some density perturbations. And if those density perturbations are large enough, then as the universe expands and the horizon gets larger, eventually the horizon will encompass those whole density perturbations, and those density perturbations will then collapse into black holes. So again, like single field, simple inflation models, you don't generate many black holes this way. But there are lots of multi-field models and other sorts of well-motivated models you can write down where you can get a fairly large abundance of these sorts of models. We can make a kind of back-of-the-envelope estimate for how big or massive these black holes will be based on when they form. And that's based on the idea that roughly the total mass, the total energy within the horizon at the time of the formation will go into the black hole. So we expect the black hole mass to be about equal to the mass containing the horizon at the temperature or time of formation. So we can do an estimate here. Our black hole mass is going to be the order of magnitude of the horizon mass. And the horizon mass is just the density and then the volume of the horizon. Something like this. And I use my first Friedmann equation. That's how it should be to go. To relate this to the energy density, which in turn reduces to this. Something like that. So black holes that form at a high temperature will be smaller than black holes that form later. You'll notice in this, I've dropped a whole bunch of order one factors, G stars, pi's, integers. I'm going to do that throughout a lot of this talk. But whenever I give you a numerical result, like I'm about to now, you can rest assured that all of those numerical details have been included like this story. So this has all of those numbers I dropped in my analytic estimate. So if, for example, I'm forming black holes as those density perturbations into the horizon at a temperature of 10 to the 12 GeV, kind of a reasonable number after inflation, those black holes would have a mass probably in the ballpark of 10 to the 7 grams. So like, picture something as heavy as a truck or something. So I can put in a couple of different temperatures, just to give you an idea. Let's say I reheat the universe to 10 to the 14 GeV. Okay, that's kind of as high a reheating temperature as you could realistically hope for. That gives me a horizon mass of about 2 kilowatts. So that's kind of the smallest black holes we're going to be talking about today. Maybe the black holes instead are forming much later, right around the time the Big Bang nucleosynthesis is starting. These would be much larger black holes. In that case, the horizon mass would be about 2 to 4 solar masses. So you could get things in the stellar mass range in the era leading up to the end. I could even consider something much later, maybe around the time of recombination. This will give us supermassive primordial black holes. There can't be very many black holes in this mass range, or there can't be very many primordial black holes in this mass range, but they can make up a small fraction of the dark matter and be interesting from a lot of different perspectives. If you want to know more about that, this paper here explores supermassive primordial black holes in novel ways. All right, so let me sketch some of the constraints we have. By the way, this chalkboard are luxurious. I'm working on the chalkboard system. All right, so here's the mass of black holes in solar masses, and here is their abundance relative to that of dark matter. It will be all the dark matter. Obviously, it can be more than that. So exceed the dark matter abundance. Way over here, on this end, we have constraints from C and B, and I'll say et cetera, because there are actually a bunch of other kinds of constraints you can put on really, really massive primordial black holes. They basically, the black holes just sit around and creep, screwing up the temperature variation in C and B, so you can't have a very big abundance here. And then you have a range like this, which is ruled out by the null searches for gravitational microlensing events. And those get down something like 10 to the minus 15 solar masses, so pretty small. And then there are constraints here from evaporation. So the idea in this mass range is that those black holes are small enough that they're actually appreciably emitting Hawking radiation now, producing things like gamma rays and electron positons that we could observe, but we don't, so we can be pretty sure that there aren't a lot of black holes in that range. This constraint ends suddenly here, and that's because black holes of that mass or less will have completely disappeared through Hawking evaporation by the present. So the evaporation time for a black hole at this value, which is about 2 times 10 to the 14 grams, these black holes will have evaporated before we reach the H. So there's a pretty interesting range there. I'm not going to talk about it, but that like this black hole window, black hole dark matter window still exists. But other than that, I think we can conclude from this that the primordial black holes don't make up an appreciable fraction of the dark matter. Maybe a little bit, maybe a few percent of that might go into or something, or maybe in that narrow dark matter window. But otherwise, we can be assured that the dark matter is not made up of black holes. As we go farther to the left, however, we reach an interesting range of possibilities where the dark matter, the black holes might not make up the dark matter, but they still might have impacted the thermal history of our universe, maybe generating the dark matter or dark radiation, or having things to do with baryogenesis or other source of phenomena that took place in the early universe. By the way, if anyone has any questions along the way, jump right in. I would love to hear what you have to say. Yes?
How big is that region you circled in terms of the black hole mass?
So it's actually a bit of a controversial region. There are some papers saying it's closed by various dynamical constraints and things, but it's probably something like 2 orders of magnitude in mass. But it's all contentious. So there are a lot of people who argue that that's not as open as I might have suggested. Yeah, Dave.
Is it remotely possible for massive, but maybe not quite this massive, black holes to seed supermassive black holes? is that
Yeah.
possible in terms of the constraints and the mass fractionality and so on?
So what I would say and what we said in this paper is the real challenge is explaining how you go from the 100 solar mass stellar seeds to the kind of intermediate mass and supermassive range as quickly as they seem to be required. Like we see a lot of very massive black holes and quasars at very high redshifts. It's not at all obvious how nature does that. The problem is, and what we tried to do in that paper was write down a self-consistent inflationary model where we could make black holes be big enough, early enough, to appreciably help that story. We were sort of successful. Okay? The model we were able to write down can do the things we wanted to, but it's kind of at the edge of its validity machine. So I'm not sure if you should trust it. But the thing I think you should walk away from that paper with is that constraints from spectral distortions in the CMB are very severe, and any black holes heavier than 1,000 or 10,000 solar masses that are primordial have to have some extreme non-bouncing energy to not inflate with those constraints. Okay, let's talk about Hawking evaporation next. So one of Stephen Hawking's most famous contributions to science was his realization that a black hole should have thermodynamic properties. In particular, its event horizon or short radius and its short black hole will have a temperature given by this expression, so inversely related to its mass, and it will radiate all kinds of particle species at this temperature, so long as the mass of those particles is below the temperature. For a 10 to the 8 gram black hole, we expect this Hawking surface to radiate as an approximate black body up to gravitational effects with a temperature of 100 TeV. So a black hole in this mass range could, without suppression, radiate the entire standard model particle content. Hot quarks, photons, Higgs bosons, all of it without any appreciable suppression. I think I'm going to really drive home in this talk. I'm going to say it more than once, so I'm warning you in advance, you get used to hearing it, that gravity is democratic. It doesn't care which particles have electric charge, it doesn't care if they have QCD color, it doesn't care if they have any interactions at all. Gravity touches everything equally, and therefore these black holes are going to give us a great way to make extremely evenly interacting particles. If I just say there's a hot thermal bath in the universe, I have to ask, which things will be populated in the bath? I don't have to ask that when I'm talking about black holes. They're going to make everything in approximately equal quantities. Okay, so I can calculate how fast a black hole will lose mass from these Hawking evaporation products. And to do that, I sum over the different particle species that are at least lighter than this temperature. And I have the strict G, which is just our normalization to our, what we call a gray body factor. And then this G star H, H stands for Hawking, is counts the weighted degrees of freedom of the different particle species. In our convention, for spin 1/2 particle, the fermion G star Hawking is 1 per degree of freedom. So electrons and positrons have G star Hawking of 4. Neutrinos have 2 per family. Quarks have 12 per family, etc. Let me actually erase that. Spin, so for a spin 0 particle, it's a little bit bigger, and that's because the black hole prefers to radiate particles with less angular momentum. For vectors, it's 0.41 degree of freedom. And for spin 2 gravitons, it's 0.45 degree of freedom. So as long as you're talking about a Schwarzschild black hole, which has no angular momentum, this will prefer to radiate at at this sort of ratios, low spin particles. So if I take this equation, I assume that the temperature is heavy enough to make all the standard model particle content, and I sum up all these G stars and everything, I get this number. So you can kind of look at these numbers and see that for very small black holes, they're going to evaporate very, very quickly. And that's going to be important to get a self-consistent picture of the early universe. I can take this differential equation and I can solve it, basically integrating from some initial mass at time 0 to a mass of 0 at some later time, I'll call it tau. And when you do that, you find that this evaporation time is about 4 times 10 to the minus 4 seconds for a black hole with an initial mass 10 to the 8 grams. So when I look at this, I will know that any black hole is lighter than, to start out with a mass lighter than about 10 to the 9 grams, will have entirely evaporated and disappeared from a universe before or around the onset of BBN, which starts about a second after the Big Bang. So the reason I'm interested in making these black holes disappear before the onset of BBN is just that the constraints on primordial black holes from BBN, from the measured light element abundances, are very stringent. And frankly, you don't want to mess with them. I wrote a long paper about this with my former student Celeste Keith. I think that's this paper. And I'm not going to go through that in detail now, but I will just tell you about some of the main things about the light element abundances that a population of black holes in the early universe could impact. First of all, the energy density in those black holes and their evaporation products just adds to the total energy density and therefore increases the rate at which the space was expanding at this era. And that means you can change the time or temperature of proton-neutron decoupling, enhancing the neutron to proton ratio before we begin subset. If you have more neutrons per protons than in the standard picture, you get more helium, inconsistent with observed ratios. The second is hadrons and mesons that are radiated from the black holes as Hawking evaporation can impact the proton to neutron ratio through processes like this. Okay. And again, if you screw up the neutron to proton ratio, you screw up the helium to hydrogen ratio. The next thing to worry about is photon dissociation. So the photons from Hawking evaporation can break up helium, and you not only destroy some of your helium that way, but you produce excess deuterium, which is actually the bigger constraint. So by producing too much deuterium, you get in trouble as well. And then fourth and last is hadro. Dissociation. So at higher temperatures above a fraction of a keV, those photons won't be able to do photon dissociation because they'll be absorbed from air production in the thermal bath. But the mesons that are produced from Hawking evaporation, those guys can still break up helium and produce deuterium. Those constraints are very, very tight. When I take all this stuff together, I find that at 1 second after the Big Bang, we can't have more than an order of 1 part of the dark matter be made of these black holes. As I go to later times, at 100 seconds after the Big Bang, it has to be a 1% fraction. And even smaller fractions as you go farther and farther off. So the takeaway from this is that the era of BBN could not have had a significant fraction of its overall energy density in the form of black holes. So there could have been a trace abundance, but not any appreciable fraction.
So if you were to interpret that plot as initial black hole abundance, that those constraints would turn into another line.
Yeah, so we're living way over here, right? So this is the abundance today. But you're right, you could imagine plotting, and people have plotted things, actually in this paper, we plotted things that are very much like what we're describing, where we have this where the energy density of the black hole is taken to be the energy density before evaporation starts. And those have contours that kind of look like this, where this is an order 1 thing, and this is the order -5 thing, as a function of time. Good. All right, so let's go on. I'm going to erase everything on the board and make some space. By all means. Good. So I think yes. So here's how I would do it. I would say there's some sort of heavy particle that on standard radiation-dominated thermal histories was not really relevant. Okay, it just disappeared from the thermal bath early on. But black holes, because of this equation, get hotter as they evaporate. So at the end of their lives, they can make these heavy particles. Maybe they make those particles. Maybe those particles are out of equilibrium and they decay in a CP violated way. So you can generate an almost arbitrary amount of CP violation into the universe if you put on a scenario like that. Then we have. If I have time at the end, I will actually show you how baryogenesis can be helped by these sorts of things. Okay, so now let's say that you've got initial conditions where you've created some black holes of some mass. Let's ask how the universe evolves before BBN in such a scenario. Well, the radiation density up to small factors, order 1 factors of G star, G star S, evolved with 4 powers of the scale factor. Whereas the black holes are just going to evolve like matter. Okay, so they're going to evolve with only the geometrical 3 factors of the scale factor. And this means that as the universe expands, the ratio of the black hole energy density to the radiation energy density will grow with the scale factor. I'm going to draw a plot over here because I'm going to keep adding to it and I'm going to include it. Here's a scale factor. Here's the energy density of a given component relative to that of the total energy density. And here's my radiation. Maybe I start up here with that black holes, but now this is going to go up as the universe expands. And if it goes on long enough, we will enter into an era of black hole domination. This is actually a pretty generic outcome. All you have to do is start with a trace abundance of small black holes that live for long enough for the universe to expand enough orders of magnitude to reach this condition. I'm not going to work out the following result, but numerically, the condition for black hole domination is that the initial ratio of these energy densities has to be greater than 1 part in about 10 to the 12 for an initial temperature 10 to the 10 GeV. In the case on the graph. So this is a small number. You really don't have to start out with a lot of black holes. When I started working on black holes in the early universe, I thought they were kind of an unlikely source of interesting early universe phenomenology because most of the inflationary models don't give you a lot of black holes. But this just shows that you don't need very many. If one part of the energy density in a trillion is made of black holes, then this ratio of a trillion could still grow to being more than one by the time those black holes evaporate, and that means really interesting things can happen as a result of those black holes.
I thought the temperature and the black hole mass are they independent of each other? Right? Previously,
Well, these are actually closely connected.
right. So previously they were related.
Good. Let me write that equation down, and then so I said before that the horizon mass, which is what you expect the black hole mass to approximately be, would be okay. So up to order one factors, you can see this all kind of holds together. I could have assumed a ratio between these things and then just written this as just the mass or just the temperature, but it would get the same approximate result. Okay. So in this sense, having a black hole dominated era in your early universe's history is something of an attractor solution. A lot of scenarios we could write down would lead to something like that. So let's continue in time and ask what happens as these black holes evaporate. And the short answer to that is all their Hawking evaporation products produce a new bath of radiation, which thermalizes, giving you conditions like you might normally expect in a radiation-dominated universe. To calculate the temperature of the universe after the black holes evaporate, you basically set the time for a matter-dominated universe to the evaporation time, find the energy density at that time, and then relate that to the temperature. If you want to do it more carefully, you integrate over the evaporation time as a function of time, the evaporation rate as a function of time, and when you're done, you get this numerical result. You get that the universe is left after the black holes have evaporated with a temperature of about 50 MeV. Again, scaled to a mass of 10 gigagrams. And it depends gently on the temperature. So this is well above BBM. That should be all okay. We don't really have any direct empirical probes about the universe's thermal history prior to about an MeV. So it's completely possible that we had a situation, going back to this, when black holes dominated the energy density, they evaporated, producing a new thermal bath at the time of those black holes of evaporation. Okay, I warned you that I was going to say this over and over again, but I'm going to do it again. Gravity is democratic. So at this stage, when all those black holes that dominated the energy density of the universe disappeared, they are going to produce every kind of particle species that's lighter than their surface temperature, which is the whole standard model and anything else that we don't currently know about that is too feebly interacting for us to notice in our experience. So maybe too heavy for us to produce it. So this is going to be a very attractive mechanism to generate things like dark matter or generate dark radiation, things that contribute to what cosmologists call impact. Another thing I want to emphasize is that the temperature of these black holes increase as they evaporate. So whereas the universe's radiation bath is colder as space expands, the black holes in that bath get hotter, allowing you to produce much, much more massive particles than the temperature of the thermal bath. So these black holes in this stage will give us an excellent mechanism, a very interesting mechanism to generate very heavy particles that would not normally be expected to be present in the thermal bath. Yeah.
I just want to know
Yeah.
what is about the numerical range.
Well, it depends on the values here, but in this case, the scale factor, what, you mean how many orders of magnitude is it more or less? So in the values I wrote down there, this might be, well, this has to be at least 10 to the 12 ratio or less, which means this has to be 10 to the 12 or less. But because this is kind of long in this sketch, maybe this is 10 to the 8. Okay? And then after 10 to the 8 or 8 orders of magnitude in scale factor, then we have a several orders of magnitude of black hole domination, and then they evaporate, and then the enters. That might be an example.
So if you were to use the black holes to make dark matter and gravity is democratic and so on, generally speaking, to get, does this generally favor dark sectors that have more than 1 degree of freedom if you want to reduce them in competitive numbers to the standard model? Is that, of course you can always have one with a very heavy mass and a very hot black hole, but in the kind of things, in the kind of black hole scenarios that are not excluded, do you tend to be drawn towards multi-sector dark sectors or multiple?
What I'll say is this, if you're worried about dark matter as
Yeah.
opposed to dark radiation,
Yeah.
the challenge is not going to be making enough of it.
Okay.
The challenge is going to be not making too much. So in a sense, you might prefer simpler scenarios. But and I'll work that out in a few minutes. So all your answers will be correct.
Okay.
All your questions will be. All right, so let's talk about dark radiation, and then we'll turn around and talk about dark matter. And what I'm going to do here is I'm going to assume that there was an era of black hole domination. Okay, the details will be inside, but before the black holes evaporate, they dominate the energy density. And I'm going to assume that there exists at least one long-lived, very feebly interacting, relatively light particle. Okay? This thing is going to make up our dark radiation, and we can calculate how much of it you should expect to be produced from these black holes. Immediately after the black holes evaporate, we expect this ratio of energy densities. So this is the dark radiation energy density, and this is the standard model bath energy density. We expect this just to be given by the ratio of those G star H's that I talked about before. So this quantity is about 108 for the standard model particle content, and this number is like 4 for a Dirac fermion. It would be 1.82 for a real scalar, 0.82 for a massless vector, or about 0.1 for spin 2 graviton. So these are just like 4 classes of particles you could write down that you might know each other this way. My view is that gravitons like probably do exist, and I imagine any kind of quantum theory gravity will say they do. So you should expect these black holes to generate those. The other 3 are just things that could exist. Okay? We don't have any evidence of them, but if they were to exist, they would be produced in this way. Then,
explain those numbers. I don't understand that factor 40 and why are the fermions so big?
yeah. So I wrote down the spin suppression factors before. I don't know if you were here yet.
I mean, you are just dealing with that.
It's weighted by the spins of the particles. So,
No, but that's not a factor.
well, where's the 40 coming from?
1 low, 4 up.
So okay, so this has 4 degrees of freedom, this has 2, so there's a ratio of 2, but the other factor of 20 is from the fact that they have spin 2 versus, yeah, the Schwarzschild gray body factors for high spin particles are quite significant.
So the gravitons don't allow in pairs.
They don't come out in pairs, but also they,
It's long wavelengths.
okay. So if you look up these tables in the old papers by Hawking and Gibbon, and et cetera.
Probably page.
What's that?
There's probably page.
Okay, well, the papers don't have his name on it, but these numbers go back to the early days of this stuff. And it's, by the way, they all reverse if you're talking about a Kerr black hole with appreciable angular momentum. So if the black hole has angular momentum and wants to lose it, it will preferentially produce high spin particles. If you don't have any angular momentum in your black hole, it will preferentially produce the lowest spin. Okay, so we start out, let's say with a dry formation. Maybe 4% of the initial energy density in the form of this dark radiation candidate. And then, as the universe expands, the energy density in that dark radiation goes like 4 powers of the scale factor, whereas the standard model bath actually has other corrections which look like this. And this just accounts, it conserves energy in the bath, it keeps track of the mass thresholds and entropy dumps that occur as temperature drops below the mass of various particles in the spectrum. So I can take these two things together, and I can work out the ratio of the energy densities. So I start with this number as my initial condition. And then I scale by this. And I can calculate this whole thing. I can calculate it, the temperature, matter ratio, quality, and I can look up in Colvin Turner, or better yet, in my new particle technology textbook coming out this spring, and I can relate this to a contribution to this quantity, then the effective number of relativistic species of neutrinos. The Colvin Turner expression looks like this. N nu is approximately 3. And these are all details I don't want to trouble you with right now, but then I put in these, and I get a number for my Dirac fermion of about 0.1. Okay. You'll notice it does not directly depend on the mass of the black hole or anything else. All it assumes is that there was a black hole dominated era. It depends a little bit on the temperature that the evaporation reheats the thermal bath to, but not very much. Okay. And it depends on this whether we're talking about a Dirac fermion or whatever. So this is like a pretty straightforward prediction. It would cover a lot of different scenarios you might want to be interested in. And this number, 0.1, is a pretty interesting one empirically. We know that from the CMB Planck data and to a lesser extent light element abundances that delta N effective isn't bigger than about 0.3 or so. So here's my initial mass of the black hole. And here's the contribution to N effective. So we have a current limit of something like this. We have an expectation that with something like next generation stage 4 CMB, we could get down to something like this. In the meantime, this expression I just wrote there looks something like that. For the whole range of masses that I'm considering here, you expect something that's below current constraints, but easily within the reach of next generation. The scalar case, well, this is what the vector case looks like, a massless vector. And then there's a scalar case here. Because of this significant suppression, however, gravitons probably won't be within the reach of planned ineffective measure. So this is pretty exciting. If there was a black hole,
So you're saying that S6 or something could get to gravitons, if that's
I think you're hitting cosmic variance probably before you get there. If you could lower that constraint, sure, but I'm not sure that's it. It's going to be there.
so they remain unobservable.
At least in the scenario I'm talking about right now. Hold on for a while. I might make it more optimistic. All right. So I want to mention one more thing before turning to dark matter. And that's before I said something about the particles I'm imagining here, these sorts of things, are all going to be light. Okay, so what I mean by that is they have to be relativistic at the time of matter radiation quality, the function of radiation. But we're used to thinking that means they have to be lighter than an electron volt or something. So that's true for normal thermal relic. But here, the black holes have temperatures that are much greater than the thermal bath around them. So these guys don't have to be all that light anymore. They can be as heavy as MeV sort of scale of mass and still be relativistic all the way up until the time of matter radiation quality. So what we might think of as a dark radiation candidate, traditionally, we can be more open-minded. We go from much 6 orders of magnitude higher in mass and still expect them to behave. All right, so let's pivot now and talk instead about dark radiation. Let's talk about dark matter. And again, I'm going to erase everything. The calculation is going to look kind of similar to the dark radiation calculation I just did. But the outcome is going to look really good. Again, I'm going to hypothesize that in addition to an era of black hole domination, we have some sort of massive, stable or long-lived, very feebly interacting particle that can be radiated from those black holes. The black holes will produce all species that are lighter than their temperature. Recall that the temperature of a black hole is about 100 TeV scaled with 10 to the 8 gram mass. So for example, if I have a 10 to the 8 gram black hole, it can produce a whole standard model that can also produce 10 TeV particles and 50 TeV particles. Probably can't produce PeV scale, at least not in large abundances. So we start out with a picture where X is my dark matter candidate. After the black holes reheat the universe to evaporation, I expect their ratio of abundances to be just like they were in the dark radiation case. And just like in the dark radiation case, this is in the order of 10 to the minus 2. So 1% of the energy density from the very beginning is in the form of these massive dark matter candidates, feebly interacting dark matter candidates. But this is a problem in this case. In dark radiation, it worked out very well for us. And to understand why this is such a big problem, consider the case of standard WIMP freeze out. Okay? So I have a equilibrium abundance here. And in the standard picture, this process, scattering, annihilation, pair production, keep the number density along this equilibrium curve until some point when freeze out occurs. And you can get the right dark matter abundance. But to do it, you have to be way, way down from that initial starting point when the temperature was greater than the mass of the particle. So you have to annihilate away almost all of the dark matter, leaving behind only a tiny fraction of its initial abundance to get an acceptable dark matter abundance. If, instead of here, freeze out had occurred here, you would have wound up with way too much dark matter. That's what's effectively happening here. So the black holes are producing order percent of the total energy density in dark matter. As the universe expands, that fraction grows with the scale factor, and it gives you way, way too much dark matter. There are two simple solutions to this problem. As the first solution, let's consider a scenario where the dark matter is a lot heavier than the initial temperature of the black hole. In this case, the black hole can't originally produce the dark matter. It's hotter, though, as it evaporates, and eventually its temperature exceeds the mass of the particle, and it can start producing it then, but only with the tail end, only the last remaining part of its mass can it produce the dark matter. So I can write this sort of picture. Here's my mass of the black hole, and here's the temperature. And there's a one-to-one relationship for a structure of black holes like this. So maybe I start here at 10 to the 8 grams, and maybe my particle in question has a mass of 10 to the 10 G. Just a bit easy to remember number. And here starts out at 10 to the 5 G. And then my black hole evolves along this curve. And only here, when its mass has dropped to 1 part in 10 to the 5 of its original mass, can it start to produce a dark matter candidate? And that effectively does the same thing that this did, the annihilations did in the standard Wimp picture, giving us a potential to generate an acceptable abundance. So, numerically, when you work this out, again, assuming that there was a black hole dominated era in the early universe, this works out to that's what I meant to say. So I'm scaling this to the Dirac fermion case, but in this case, that order 1 factor doesn't matter much. Okay, so I can get the desired abundance of dark matter, the measured abundance of dark matter, for order 1 factors here, super heavy mass here, in the ballpark of 10 to the 10 to the 11 GeV, and 10 to the 8 black holes. So I go back to my plot here, and now in addition to producing this radiation, I produce 1% of it, or less than 1% of it, in dark matter, and it goes like this. And here, this is not matter radiation quality. And that works just fine. So I said there were two solutions to the overproduction problem. This is one, by having the dark matter be very heavy. Another is maybe there was never a black hole dominated era. There were some black holes, but never enough to generate a black hole dominated era. So maybe instead of this picture, it looks like same axes, but something like this. Here's my dark matter, and my black holes, and just like that. Okay? So the black holes never dominated the energy density. They produced enough dark matter through their evaporations, even though they were a small fraction of the overall energy density. Both of those are possible. So you wind up with a situation.
This is obviously the sort of homogeneous picture of how everything is happening. How much inhomogeneity would you expect?
On any measurable scale, none. Okay. Every volume that we can meaningfully measure has a very, very large number of black holes. So it's at any scales that we as cosmologists can measure, it's completely homogeneous. I'm sure that if you went down to some microscopic scale, it would be different. But nothing that we need to worry ourselves about. All right, so here's my initial black hole mass. In that sort of scale. And then here's my initial condition. This is my ratio of black hole to radiation energy densities at 10 to the 10 GeV. So we know from BBN constraints we can't live over here. But I can draw now on this plot contours for different dark matter masses where I get the desired abundance, maybe all the dark matter. So let's do 10 to the 11 GeV, something like this. It looks like this. Okay. The break in that curve comes from the fact that on the upper right side of this, you have a black hole dominated era. This equation holds. Down here, you don't. Okay. So as I go to lower and lower masses, I do something like this, and I can go to lower and lower and lower masses for smaller and smaller initial abundances, and I can make 100 GeV limps or something, well not limps, but 100 GeV decoupled relics you can use with a tiny, tiny, tiny initial abundance of black holes. And I can also go up heavier and heavier particles, approaching the quantum state. I could even imagine a scenario where you had a black hole dominated era, maybe something like in this parameter space, you're actually producing long scale relics. Maybe these are the endpoint of Hawking evaporation. But those can make up the dark matter in such a scenario. Okay, so those are some of the main things I wanted to tell you about today. But in the last 5 minutes, I'm going to tell you about two kind of variations on this thing. So two other things you can do that I think are interesting in this kind of playground. First of all, I've been assuming this whole time that the black holes in question are terrestrial. There's no appreciable angular momentum. But you could imagine a scenario where the black holes formed, and then, because there were so many of them, their abundance was so high that they would form binary systems, and in spiral, merging, producing black holes that were not low in angular momentum, but were pure black holes. These would be, you have an appreciable fraction of their energy in their rotational angular momentum, and then these would not have the suppression when they evaporate to high spin particles, allowing us to do two really cool things. First of all those mergers can produce a background, a stochastic background of gravitational waves. They would be difficult to observe, but things like the Big Bang Observer could maybe detect these in certain parameters. So they're another interesting observational consequence. And then also, because they would preferentially evaporate to high spin particles, this would produce an interesting background of gravitons. These gravitons would still exist in the universe. They would be bathing in them kind of like the CMB or the neutrino background. But unlike those backgrounds, these would have like a KeV scale temperature. They're called the hot graviton background for this reason. And the reason it's so much hotter than the CMB or CMUB is that they were radiated from the hot surfaces of these black holes. They were not part of the standard model.
KV back at convention.
KV now. Yeah. So these are, a million times hotter.
That's good. Leaving your hands, can you describe how the inhomogeneous entropy develops in this scenario?
I don't think I understand the question.
So the point is, the black holes are serving the purpose of effectively locking into a go-go state of which then decays. You can do that with particles, but that black hole. You just have the particles. The interesting point about that is that you get those who are last night, the operative wave, this is the action of the cosmic superweb, in which you would have an entire cosmic web development that would, yes, produce at rare points, but through gravitational collapse, give you the black holes. But before that, you would have an entire picture of an evolving cosmic web with its filaments and other things. It's just that the time scale that it develops over is relatively short because of the nature of its time.
Good. So,
So it seems like there's another scenario in which the fundamental thing about why I have never really jumped up and down about PDH, despite one of my best friends, it is because of the remarkable inefficiency that is needed to try and produce it from a radiation pathway, which is characterized by I guess, 12. But this has always been difficult. We have seen so much fine tuning. And we get away from it by saying it's so dominated by the black holes, it has no memory of whatever that early radiation was. And then it's all completely at some stage.
yeah. So,
But it's concentrated black holes, and that's not the way the black holes go.
what do you mean by concentrated?
It means that you're envisioning a scenario in which the black holes are basically almost the sun. And so the whole
There's
concept
spatial
of the
distribution.
interconnectivity of the black holes that are clustering together and all of that stuff.
So we
will
just
still
took
be
their,
operative. I mean,
we took their average number density to be uniform when we did our merger rate, or our capture rate, binary capture rate.
well, that's reasonable if they're extremely rare. But if it's going to become dominated, then the power spectrum that gave rise to it is going to impact on the clustering. And clustering is going to do exactly what happens with the evolution of black hole mini clusters in
Okay, and if you were to look on spatial scales, where there's on the order of one black hole or two black holes or something, then you would find a big departure from homogeneity in this scenario, I agree. But those scales would be extremely small. Like, we don't have any way of measuring anything on those scales, right? So I think we're
where it develops, unless the public Crag stops it.
Well, we should chat further about this. I mean, I don't think I'm answering the questions you're asking. I'm not sure I understand the questions well enough, but we get to the bottom of it.
Try to create a new scenario, which says, it's because it's the either or that people who play the PDH game have always played. And it means that, some people play the game of, in order to get this observation, we need them in this tiny mass range, which I thought was.
You can take anything I've done today and generalize it to a spectrum of black holes. For the sake of simplicity, I'm not doing that here, but you can easily generalize that.
Well, that's actually a whole phenomenon, because then you get this and therefore you end up flooding radiation in the whole sequence. And effectively, the way one used to look at this is that you would drop off a very probably the dominant grouping of early black holes, because they will evaporate at that point.
That's also
I will say, like, I was wondering about the fine-tuning aspect here, but to be honest, I don't quite see it. I mean, because,
You should.
well, everything
It's
is
really a big deal.
roughly linear with black hole mass, no matter which direction you go.
So
Everything depends on linear or just some power law with black hole mass. Even if you're relying on the dark matter being heavier than the black hole when it starts being created, then you're not feeding off some Boltzmann tail. You're just waiting until the black hole is small enough to make them unsuppressed, and then you have some well-defined mass fraction of the initial black hole that ends up in dark matter. So everything here is sort of modest power laws. You don't have to tweak. and everything is monotonic, so you don't have to tweak a parameter to, exponentially, finally, in order to be.
Just to be
within
clear, we
a
run our
range.
code for big model distributions over many orders, magnitude, and mass. It's all fine. It isn't been qualitatively substantial.
So you have parallel dependencies, but I don't think you have classical fine tuning. That's
classical about it.
sorry, I mean,
It's
in
a
the,
real fine tuning that is needed in order to have black hole dominance in a universe.
So what's the tuning? What parameter can we do?
It's that sort of efficiency. Efficiency is limited.
Well, that just depends on the amplitude of density variations, right? If you take in
Yeah, but
very large.
as you know very well, you require extremely large structural flow in order to actually get something that's going to be a black hole. Usually, it's not anywhere close to that.
Yeah, and that was
But
my
that
initial
doesn't mean that
condition.
it's not of interest. It means that that's an understanding that we're in quest of.
It's well, very representative of the constantly always on top.
Usually, black holes are supposed to be black holes.
All right, so I just have like one more page of the variation of the theme I want to mention, and then I'll let you all go. So the idea is that Gordon and I worked out in it's not even on here, 2010. I don't mean that 20. It's in 2020. We were wondering whether you could facilitate baryogenesis through this sort of scenario. I think that was the nature of your question before. So we were doing it in the context of classic gut baryogenesis. So if you go back to the 1980s and read textbooks on this stuff, gut baryogenesis was like the leading way that people talked about tonight. The baryon symmetry. It's fallen out of vogue for a number of reasonably good reasons, but it turns out that if you have black holes in the picture, those reasons go away and you can make gut baryogenesis work easily. So the idea of gut baryogenesis is we have these supermassive bosons, maybe to the 15 or 16 GeV. We call X and Y bosons, and they're produced in a thermal bath, they fall out of equilibrium, and then they decay in such a way that violates baryon number and violates CT, etc. That gives you a way to address all three or satisfy all three of Sakharov's conditions for baryogenesis. The problems that these have been shown to face is that the weakening temperature in standard inflationary models isn't, generally speaking, high enough to produce a thermal population of these gut bosons, especially as proton decay constraints have forced up the scale of baryon implication. And then the second problem is there's a process, a non-perturbative process in the standard model called Spalaron washout. This is efficient at temperatures above the electroweak phase transition, so above hundreds of GeV. And what these Spalarons do is they change the net amount of baryon and lepton number while keeping the difference of baryon and lepton number fixed. So if I write down a simple grand unified theory, like one based on SU5, I would generate some baryon numbers, a lepton number, and a wash in the Spalarons would just destroy it. It would erase it long before you get to the electroweak phase transition. So these were problems facing this class of models. But now, if I have these black hole dominated era, I automatically get the heavy particle production, even if the temperature of the standard model bath is low, as the black hole temperature increases as the time. So you solve problem one. You avoid Spalaron washout because even though the temperature of the black hole is high, the bath of the radiation is well below the electric phase transition, so Spalarons are inefficient. And then thirdly, whereas you have to worry about whether the X and Y particles decay out of equilibrium in the standard baryogenesis picture, here they automatically are out of equilibrium because they're much, much heavier than the temperature of that. So all the problems that people cited when abandoning gut baryogenesis in the late 80s, 90s, early 2000s, those problems can conveniently be addressed or reconciled if you have a black hole dominated. So just to summarize some of the takeaways, if you only walk away with these three things from this talk, I'm happy. I think my work here will be done. First of all, if you start out with a tiny fraction of energy density in black holes in your universe, those can very easily lead to a black hole dominated era as the universe expands and the fraction of the energy density in black holes grows. Two, if you have a black hole dominated era, and there exists some sort of light, feebly interacting, and long-lived or stable particle, that particle will contribute significantly to dark radiation at a level that probably is below the current constraints, but is likely to be within the range of that stage 4 CMB measurements. And thirdly, you can generate dark matter in this way. You actually have, the biggest challenges are not producing too much. But if the dark matter is really heavy, or if the black hole abundance is really low, you can generate the right abundance. And it's a natural way to make very heavy particles which have very, very good interactions. All right, thank you all for your attention. I've enjoyed this. You've been great hosts here at CITA. I look forward to interacting with as many of you as possible in the couple days ahead. Thanks.